I'm Dave Quigley. A little bit of background about me. Currently, I work for a company called KeyW Corporation. It is a defense contractor that does work for the U.S. federal government. I, for the longest time, used to actually work for the National Security Agency on the SELinux team. So there's a bunch of stuff that I helped develop in this talk. A lot of the stuff we're going to go over today is the fundamentals that were long before when I showed up. But if you're using CentOS 7 and RHEL 7 recently, one of the features that is new to RHEL 7 that I worked on for a good 5 years straight was NFS v4 support for SELinux. So now you can use SELinux with NFS mounts where you couldn't do that before. And that was a long and painful road through the IETF to get that finally standardized and accepted into the Linux kernel and merged into RHEL 7. So let's get started. So here's the outline for the talk. There's a lot of sections here. We're going to try and blow through them as quickly as possible so we can actually do hands-on stuff and I can answer as many questions as you guys have. So we're going to go through the basics first. What is access control? Does anyone have an answer to this that's not on the slide up there? So it determines how resources that the system have are accessed. Who or what can access what files, directories, all sorts of other things within the system. So this is what you're used to. So user is Dave, me. That's my identity. I log in with my Linux account with that. I put in my password. And when I run programs, I'm run as Dave. So this is what we call discretionary access controls. This is the traditional Unix way. This has been since Unix was first set up, except Unix didn't originally have permissions, but we'll go past that. And as long as I own the resources, Dave has access to them. It doesn't matter what Dave is running. I could be running Firefox, I could be running Apache, I could be running Evolution. The files are owned by Dave. I'm Dave. I have access to them. Well, this doesn't work very well. So we're going to talk about what kind of access controls SELinux uses. And these are what's called mandatory access controls. Normally, this was kind of delegated to systems that were used by the U.S. government called trusted operating systems. So trusted HPUX, trusted Solaris, if you're familiar with that. And the idea is it doesn't really matter who's accessing the file. It matters what program's accessing the file and for what purposes. So Apache doesn't need access to all the same files as my mail client does. My web browser doesn't need access to all the same files as my database engine does. So because of this, we assign additional information to the action that's being done, and we can differentiate these actions across all sorts of different types of objects. So before, the only thing we really cared about were files, directories, and borderline some sockets, whatever sockets were exposed in the namespace. Now we care about everything. We care about sockets, we care about device nodes, we care about all sorts of other types of objects that we want to actually control access to. So the next question here is, well, what is SELinux then? I just told you that we're going to do this new type of access control, so what is SELinux? SELinux is one of these new types of access controls. It uses security labeling, which means everything in the system is given a label. And a label contains all the security information that's needed to make an access control decision. Every process has a label. Every what we call object has a label as well. And objects are things like your FIFO pipes, directories, files, symlinks, sockets. And what's interesting about SELinux is we can actually differentiate between the types of sockets you want to use. I can give TCP socket access to a program, but not UDP or ROS socket access to a program, which gives us this very nice fine-grained ability to implement good security policies over the system. So the policy is these rules of how we're going to act, how the processes can interact with these objects, and the most important thing is this is enforced by the kernel just like your normal permissions are. So the kernel is your trust boundary for the access control still. So I told you to install CentOS because CentOS and RHEL are basically your best bet for a stable SELinux distribution. Fedora is very good if you don't mind the slightly less stable nature of Fedora. However, I run Fedora for everything, including my work, so it doesn't really matter. This is a chart of how you get SELinux. If you're an Ubuntu fan, it's very easy for you. It's apt-get install SELinux. The only thing is I'm not sure if you have to go into your grub config and switch over from AppArmor to SELinux or if it does it for you. Debian, there's a long, drawn-out guide. Unfortunately, it's not as easy as the Ubuntu one is. Gentoo is in hardened Gentoo, and OpenSUSE. I had to update just the number because unfortunately their support hasn't gotten much better in the last 4 years. So if you're running OpenSUSE and you want to use SELinux, you can do it, but it's not as well integrated as the other platforms. So I'm telling you that we have this new form of access control. Still kind of difficult to understand what it's doing. So let's just see some basics on it. And so the basic thing is I want to interrogate a system and find out, is SELinux on? And if so, how is it operating? So if you have the VM brought up, you can check out these commands. And your two basic commands for finding out the status of SELinux and determining the policy enforcement mode are SEStatus and your get enforce command. So SEStatus is going to give you a whole bunch of information here. It'll tell you whether or not SELinux is enabled or not. So if SELinux is completely disabled, that first line is going to say disabled. It'll tell you where the SELinux file system, which is how the user space communicates with the kernel, where that's mounted. It should always be /SELinux. It was moved from there to /sys/security/SELinux, I think, at some point, but that legacy symlink should always be there for you. So you should always be able to just go to /SELinux and poke around. Its mode, which is enforcing or permissive, which we'll go over in the next slide, and what policy version you're running and the policy name you're running. And for when we actually go and look through a policy directory, the policy name will help us find that directory and where the policy is located. And get and set enforce are your simple, turn the enforcing mode of SELinux on and off. So what does enforcing mean? Well, because the policies aren't always written properly, you may need to have the system be in what's called a permissive mode, which is I want to perform all the access checks, but I don't want them to get in the way because I know my policies aren't up to snuff yet. And we'll find out a way to do that on a finer-grained level later on. But on an entire system level, which some people aren't always comfortable with, jumping into the deep end with cement shoes on and hoping they can swim. So enforcing mode means I will always check my access. I will always enforce the results. So if I say that this is denied, it will be denied, and I'll return that back to user space. Every single time you get a permission denial in enforcing mode, it will get thrown out to your audit logs, which in contrast to permissive mode is very different. Permissive mode says, I will perform the check. If it fails, I'll say, I don't really care. I'm in permissive mode. I'll tell you it succeeded anyway, but I will write out an error log to the audit logs for you to look at later. This will only get recorded once per class of denial, and we'll go over what that means later. But so, for example, if you failed to read a file with a specific source and target labels, it will only show up in the audit log once until you refresh the audit daemon. So it's possible that you've been working on your policy and all of a sudden you think something's working, but it's not, which is why you need to be careful of that later on. The very important thing about permissive mode is it is not providing you any real protections. It may provide you some audit capabilities where you've found out something's gone wrong, but in reality, it is not actually denying anything. You are at the same level of protection that you are if you were not running SELinux at all and you were just using your default Unix permission set. So setting enforcing mode, by default, it will look in etc SELinux config, I think it is. Yeah, for the line in there and set in your init system, which on RHEL systems is Dracket, it'll load that. Sorry, that's your init RD system. It will parse that line, say, should I be an enforcing or permissive? Should I be on or off? And then it does magic before the system's brought up to make sure that that gets done. Alternatively, there's always the kernel command line options that you can do, which are enforcing equals 0 or 1. You can also do an SELinux equals 0 on the kernel command line if you really want it off for good. It's really no different than putting it off in the config file, though. It unregisters the hooks and everything just the same, so it's not a big deal. At runtime, we can set these things using the set enforce command. You'll see that it supports 0 for false, 1 for true, and it also supports permissive and enforcing as keywords that you can set. And if you want to poke around in the SELinux file system, you could echo 0 or 1 to SELinux/enforcing. And in reality, behind the scenes, that's what the tools are doing. They're using this file system to communicate with the kernel to do this. Now, you may have a question of, well, why are we using a file system to do this? Why aren't we actually using syscalls or something like that? And for a long time, there was a push from the kernel community not to introduce new system calls into the Linux kernel. Unfortunately, or fortunately, depending on how you look at it, that's no longer the case. So back then, everything that they wanted you to do to interact with the kernel was through what they call pseudo file systems. They're not really backed by anything at all. They're just device nodes that you can write or read to, depending on how you implemented them, that interact with the kernel. So that's why everything that you see SELinux-wise is done through the SELinux file system to get to the kernel. So if you want to, you can load up your VM, do get enforce or an SE status and see what it says for your machine. Poke around using the set enforce program to turn it on and off. But just make sure that it is back to enforcing by the time you are done. Otherwise, the labs we're going to do later on in the tutorial are not actually going to work the way they're expected to. They're not going to fail for you at the right times. You may still get the denial message saying something bad happened, but they're not actually going to fail for you. So while we keep going on, you guys can mess around with that. So I've been saying security label, security label, security label. I haven't told you what it is until now. The security label is all the information that SELinux uses to make its access control decision. So here is the output of a command, of an ls command with the $Z flag for etc password. And on the left-hand side, you're going to see it has all the traditional discretionary access control components. It's your user, your group, your other permissions, who owns it, what group owns it. But now we have this big extra blob of information, which is the SELinux context. I will use the term label and context interchangeably throughout the rest of the tutorial because really they're just two words for the same exact thing. So we're not going to go into too much depth the user and role components of a label because in reality the type, which is the third component there, in this case the etc, is the main workhorse of SELinux. It's what allows us to do enforce things like least privilege models on processes and have that fine-grained access control for processes. So if we want to see the labels in our system, most of the core utils packages have been augmented with a -Z option. And this -Z it's not SELinux specific. So if you were to use something like SMAC or any other label-based LSM, so the Tomoyo guys have something similar for, I think, PS, you will see that it's basically additional security information on the file or whatever object that you're interacting with. So for files, if you do ls-z, you're going to get that extra line information that we saw before. PS and PS tree, you'll get to see what's called the process label, or which we'll also call domain in a little bit. And that is, that'll tell you what security domain the programs are running in. And also you can see some stuff on ports with the SE Manage tool, which we'll actually be using hands-on later. One thing that is interesting to know, netstat does have a -Z option, but it does not show you the label of the port you're listening on. It shows you the label of the process listening on that port, which was very confusing to me, and I'm not exactly sure if that's really the right thing to be exposing, because you kind of want to know what the port's labeled itself, not necessarily who has access to it at that point. There might be a good case for adding more switches in there to see additional information, but just don't be confused if you see a domain label on a port using netstat. So does everyone have a machine that they can poke around with at this point? Everyone have a... So these initial labs you could do at least with a base CentOS install. You don't need any special RPMs or anything like that for the later labs. Do you... So the username on the VM is SEDemo, and the password is SEDemo, and the root password is SEDemo as well. So something that you should do is just look around your file system in this lab. Just look around what it's in opt and var and etc, particularly var run, because depending on the configuration of the system, you might see a generically labeled file in var run, but you may also see a per process labeled file in var run. So there's a lot of, it's interesting to see what labels are on what files in the system, so that, for example, if you think your PID file is special, If you don't think anyone except for your process should be reading your PID file, you may want to have a program-specific PID file context. So instead of just being PID_T, you may have MySQL PID-T as your type instead. And later on when we do policy development, one of the things that you need to think about is how special are my resources? Do I really need them not to be accessible to everyone else on the system or not? And then that allows you to reason through what kind of labels you want to have in your policy. So I can probably also do this from, so. That looks like a reasonable size up there. So for example, ls-z var run. So is there a, yeah, so if we look, policy-wise, you can see var run t is a generically labeled file under var run, which are all the PID files. But apparently a lot of these daemons think that it's important to isolate their PID file from everyone else. So Network Manager has a Network Manager var run t for its PID file. So it's good to poke around the file system and look at all these types, and we often try and label them as closely to their domain as possible, so you shouldn't ever look at a type and go, I have no idea what program this belongs to. So, and then let's look at PS. Oh. So, something that you're going to see flooded through the first page, anything that's a kernel thread has a special type associated with it. It's called kernel T. If you see something running with kernel T, you can pretty much assume that's a kernel process and not be too concerned with it. But you can see, and these are domain types here because they're assigned to a process and not to a particular object in the file system. So you can see all the different types that programs are being run in. And this is what is part of the policy rules that says this type can access these other types. So if you're writing policy and you notice things aren't going right, you could be like, well, am I even running in the right domain to begin with? And we'll debug that kind of stuff later. But this is just a poke and prod around the system, start to learn about your types, start to kind of see what's actually going on in your system, because it's very opaque initially if you don't have someone helping you hands-on figure out what's going on. You could be like, it's just a whole bunch of information, I don't know what's going on with it. And that's that. Was it that? Yeah, those. All right. All right. Does anyone want more time to poke around stuff, or are they happy with moving on? So if you have questions at any point, don't let me just ramble through this stuff without answering your questions, because the last thing I want you to do is actually get to a point where we're going to be fixing a problem and still not understand what's actually going on. What do you mean what labels are? All right, we can, so, yeah, so the what labels mean and how they're used is basically what we're going to cover in the SELinux fundamentals section. So the security model that's the main workhorse in SELinux is something called type enforcement. And as you can tell by the fact that we've been talking about types all this time, it's really important. So it's the core security model. It's what actually allows us to bind permissions and access to individual programs on the system. So the first important concept is a domain. A domain is a type that is assigned to a process. The idea is this is the, if you were to think of security policy as kind of like a graph, or maybe like a Venn diagram or something like that, It's a big bubble which describes your process. And access to resources are what we're going to actually put inside this bubble. So the domain would be kind of like a big circle. And if we want to access files under Etsy, we'd write a rule that brings in those resources into the bubble. So that's one way of thinking of security domains. Now, this domain is also what's going to be called the subject of an access control rule that we're going to write. So it's the person that's performing the action, or in this case, the program that's performing the action. Before, we thought, what was the user performing an action, right? That's your traditional way of thinking in Unix, right? Dave's performing the action, root's performing the action, the SE demo user's performing the action. But in reality, this is not a good idea because that doesn't give us any differentiation between what any of these users are doing. So the domain types is that additional bit of information that allows SELinux to say, okay, Dave may be doing this, but in reality, this program is doing it on Dave's behalf. The Apache process running as Dave is serving up content. The evolution process running as Dave is accessing his email. And that's the purpose of this is so we can tighten the permissions needed to just a set we need. We can tighten what's allowed by a user down to just what the program is using. And this domain type is what allows us to actually get that first step in doing it. It's what binds the process to a set of permissions that we actually want to use. So, for example, the password process runs in its own domain. And it's a very special domain because it's really the only domain that has access to write to the Etsy shadow file. And because we've written policy in a certain way, it's the only thing that has access to it. So the takeaway from this slide is a domain is the label assigned to a process. Now, the types, which in a sense are also security labels themselves, are what we're going to assign to what is technically called an object. Objects are things in the system which we wish to restrict access to. So a particular file gets a security label. Directories get security labels. Sockets, IPC channels. Your semaphore. We have policy rules that allow you to specify whether or not a process can create a semaphore to talk with another process. Things like file descriptors have labels. So it may seem confusing at first, but it's what allows the policy to write these very fine-grained access matrices to determine who can access what files. Now, the takeaway from this is that types are assigned to resources that we wish to act on. So anything in the system that we wish to perform an action on will also be given a security label, and it will be called a type at this point. Now, something also to think about here is if two things share the same type, they're really the same object from a security perspective. So when I said earlier that you need to think about whether or not you want a specific type for your objects, so for your PID file, if you think that it needs its own var run t label, you need to actually think in your head from a security perspective, how important is it to me to isolate this file from everyone else? Yeah. No, it's by convention. So by convention, all the user tokens have an _u, all the role tokens have an _r, and all the type tokens have an _t within the security context. I do not believe so. I'm pretty sure there's nothing in the policy toolchain that requires that you have those things in there. A lot of the tools, however, have been written to assume that convention, but there's nothing in the kernel components or the user space components themselves to actually enforce that your types have _t. It's just a by convention for ref policy. And I'm sure if you wanted to write a policy from the ground up, not using ref policy, you wouldn't have to do that at all. So let's look at the difference between what a domain and a type is, because you're going to look at me and you're going to go, well, they look the same. They look like a full security context. Why is there a difference between a domain and a type? In reality, the difference is how they're used, not their construction. So the use of the domain is that we're going to put it on a process, and the use of types are they're going to be on things we want to actually act on, the files, the sockets, everything like that. So from an actual reading the context perspective, you're not going to see much of a difference between these two things. by convention, the domain type of a process will always be labeled the domain, the process name underscore T. So, for example, Apache, because Apache's process name used to be HTTPD, you'll find the type for Apache to be HTTPD underscore T. And likewise for things like MySQL, MySQL T, Postgres T, stuff like that. What we've been talking right here is mainly a semantic difference. It's how we use the label. In reality, there is no difference between a domain type and a type, except for how it's used. So from that perspective, from looking at a label, you can look at that type token of a context and know that it's always the same underneath the hood. There are special cases where you will use a domain type as the object type as well, but we're not going to talk about those because it's like we said here. For example, signaling and IPC uses that as the target type, but that's more complex and we're not going to need that. So right now we have two types. We have a domain type and just a regular object type. And that kind of allows us to label things in the system. Processes have domain types. All the other objects have target types. Now, I've been telling you that we can actually differentiate based on the types of things that on the objects that we're going to be accessing in the system. And what allows us to do this is a fundamental concept called an object class. The object class, which will be a component of the policy rules that you write, basically allows you to differentiate the type of objects that you want to provide access to. So let's assume that you use the same label for two objects for its target. You can actually say this allow rule allows me to do process-related stuff. This one is file-related. This was directory-related. So in normal Unix permissions, as long as you have read and execute on a directory, you can get into it. You can read the objects, the files that are listed in it. And with SELinux, you can actually say, I only want to allow them to search through the directory. I don't want to allow them to actually read all the objects. And it's kind of difficult to see at first, but when we write the policy, it'll be a little bit easier to see. But another interesting purpose of having object classes this way, I told you earlier that you can bind to TCP sockets, but not UDP sockets. It's the object classes that allow you to write rules like that. So let's say you want Apache, you have a process, it only needs access to TCP sockets. So if someone exploits your service and wants to create a UDP or a raw socket on it, they would normally be able to under the Unix permissions. But because we write SELinux policy to say the only type of socket that I can bind to is a TCP socket in the policy, we can actually restrict exploits like that from working at that point. So in the policy rule, you're going to see subject, domain type, target type, and an object class with a set of permissions. Now, these permissions can vary based on the object class. For example, socket permissions look very different from file permissions. Well, not hugely different, but they can be different. So, for example, file has unlink, where there's no reason for a socket to have unlink. Sockets have connect and accept, where there's no reason for files to have that. So each set of object classes has their own permissions that you could write policy for, and they're very specific to the object class itself. Whereas traditionally in the Unix model, we really only had read, write, and execute. And if we had a socket that was mapped into the namespace, like some sort of named pipe or something like that, you really only still have read and write on that socket that you could restrict. This we can provide finer-grained access. So for example, let's say you don't want to allow your main, let's say you have a daemon that's structured where you have a fork off a child process for processing workers. You don't want the child process itself to accept the connection. You only want the main process to accept the connection, hand off the file descriptor to the child process, and do work. You can do that with this, because now we can actually restrict who can do the accept, who can do read and write on the socket that I've been given a descriptor to. So these kind of fine-grained permissions allow you to have better structured programs that you can bracket down the permissions you need for a child to actually do work and write them more securely. So I've talked about objects, object classes, and permissions. This gets wrapped up into something that we're going to see lots of when we have denials, which is called the access vector cache in SELinux. Access vectors are just a very fancy word for saying this for group of information. What process is accessing what resource, label, we're talking label-wise here, we're not talking actual discrete resources, with what object class and what permissions. Inside the kernel, there's the access vector cache, and it has these tuples in there that say a source type, a target type, an object class, and permissions that are allowed. And the kernel stores this information, and when you make an access control decision, it goes, all right, what process was making this check? It's Apache. What are they trying to make it on? It's this type that Apache has associated with its web content. Okay. It's asking for a file access, and it's asking to read. So it goes through this tuple, it looks at the bitmap for the permissions and says, do I have access to this? And then the kernel will say yes or no. Another thing that's interesting is SELinux provides several other kinds of rules just rather than allowing access. So there's another rule called audit allow. So this allows you to audit the access to files as well. So let's say you had a special Apache content domain that you wanted to audit whenever someone wrote to it. You could write an audit allow rule in the policy to say, whenever this rule succeeds, whenever someone tries to write to the special Apache content domain, just dump an audit log message for me. So this is good from the perspective that if we have content that we see is very vital, for example, let's say we're a PCI compliance company, and we want to make sure that we're keeping all of our PCI secure. I don't know if you know what PCI compliance is, but it's credit card processing basically, and it's very, very in-depth requirements for how you handle and process credit card data. Let's say you wanted to make sure you always knew when the database was written to, always, because you have some sort of regulatory compliance issue with that. You could say audit whenever this access happens, so I can go back and say what happened, who made the change, when, does it make sense for that change to have happened? So in the audit log, we'll see an example of an audit log entry later on that shows that. But there is, so the audit subsystem in the Linux kernel handles just more than telling you that SELinux had a denial. It handles these audit records as well. So SELinux makes use of the regular audit subsystem audit logs to dump out these audit allow messages. So you'll see a record in in varlog audit. Yeah, varlog audit d audit.log, I believe it is, saying that this file was accessed. And it'll give you it'll give you the security context of who accessed it, the file's security context that they were accessing. We'll see what an audit log message from SELinux looks like later on. But it gives you a lot of information on who did this, when, and through what means. So this is a very clinical example. It's the bare minimum needed to showcase why we can restrict programs the way we do. So, for example, the password program is pretty special, right? You know, it has one job: take a new password, update the password file, and particularly, more importantly, update the etc shadow file, which is where the passwords are stored. So, we need to make sure that the only person in the system that can access the etc shadow file is the password program or another set of very select programs that are charged with modifying it. So the idea here is that SELinux is going to so one thing that I haven't mentioned so far is SELinux is a deny by default system. So reality in these policies, what you're writing is you're describing the state of what you believe a well-running system to be. You know, what permissions should the system behaving properly actually need to do its job? So in this case, as you can see, the password process has what kind of type? Domain type. And that domain type is passwdt. So we write rules for the password program that use that as the source domain. And so I'm trying to, I just realized I never actually explained type transitions, domain transitions to you. So this slide's actually probably 2 slides sooner than it should be. So let's move on to those 2 slides and then we'll come back to it. So that slide makes very little sense without knowing what a domain transition is. So I actually flip-flopped those 2 slides accidentally. The idea is, back in the day when we had these original trusted operating systems, you used to have to say things like, I want to run this program at this security level or with this security context. And everyone realized that that doesn't work. It's really a very bad way of running the system. You don't want to have the user have to know exactly what security domain to run their program in for it to work. So a way of handling that is they came up with something called the domain transition. And the idea is that if one process executes another process, you want that second process to be started in the right domain without any user intervention, right? If I type passwd to change my password, I don't want to have to know the domain type that passwd is running in. So in the policy, you write these rules to say when process A executes a file with this label, the resulting process is this second one. So in this example, this makes sense now because we're running our shell in a domain called user T. So that's what we're running our processes in so far. And we have some special rules here that say that user T can execute the file passwd, because that's what its target type is. And there's another rule that previous systems didn't have, which says this is a valid entry point to get to this new domain. So what's really cool is, yeah?
How can you see your own user T that you run here?
If you do ID-Z, you'll see the domain type of the shell you're running in. You could alternatively find out what your PID is for that shell and look at it through PS-Z as well. So this is where it gets difficult and kind of overly clinical and some people get lost. So this entry point rule says that when executing this file, it is possible to transition to that domain. So you want to also restrict who can get into the password domain, right? So this description has never gone well in the 6 years I've given this talk. So the takeaway from this slide is we need to restrict who can become the password domain type. And the way we do that is through the entry point rule. And particularly the way we allow this to happen without any user intervention is what's called a domain transition. So it's probably easier if I just show it to you instead. So for example, we can see currently that my shell is running as a type called unconfined T. So this is because we're running a more permissive version of the system. But there's a rule in there, like in that chart that I just showed, that says when unconfined T runs the passwd command, will become the right domain. So if I do passwd and don't type in anything yet, open up a second terminal, you can see the transition. That happened. And if we look at this, and more importantly, if we look at this in PS tree, let's see, not grep less. If we look at the parent of passwd, it's that bash process we were running as. So these domain transition rules are what allow us to start up the programs in the right domains. Another use case that you'll see of this is for example, when you start something up with an init script, because the init program runs in its own domain. It's init rc_t. And you need to make sure that the init script, or the init system, can start up domains in their right domain. So when we write policy, we'll see that there's a little interface we can use to say, when the init system starts up a program with this label, make sure it enters this new domain. The importance of doing this way is that we can ensure that programs that are run correctly in their domain. Because without these rules, you'd have to have the init system manage this by hand. And there are times where the init system doesn't handle this right, and you used to see old domains set up in init rc_t. Like you'd run Apache in that domain, and it would just fall on its face because it makes no sense to run it in that domain. So, any questions besides?
What happens if you
So it will inherit the security context of the process that execed it. So, for example, there are rules. So there are interfaces that allow you to exec a domain exec a file without actually transitioning into its domain, and at that point, it just gets run in its parent's domain. And we'll see those interfaces when we actually start the write policy. Now, we're going to blow through this quick because in reality, you don't use this very much. You can. So I recently reviewed a book that should be coming out in the next few months called, I think it's the SELinux Cookbook. They go into this very well, proper role separation within SELinux. But for the most part, you're just going to basically be tossing your domains into pre-existing roles anyway. And the idea is, in traditional role-based access controls, you set up things like your database admin, your web admin, stuff like that. And using whatever system you do, you assign particular actions that they can perform. In SELinux, it's a little bit different. Instead of assigning the particular actions, the roles are sets of domains that you can have access to. So if you want to provide a domain that provides certain functionality, you bind that domain to the role then. So if you want the web admin to be able to perform certain actions, you just assign the types that are allowed those actions. So for the most part, you're going to run as an unconfined role in SELinux. Your system utils will just run as probably sys system R, and you should really not be concerned with this too much. Once you actually get into very advanced usage of SELinux, you can create new roles and bind them to new users and create advanced user roles in the system. In reality, you're not going to do that. There might be frameworks that do that for you, but by hand, you'll very seldomly do it. And the last component of SELinux fundamentals, before we move on to figuring out what it's telling us and how we actually fix those problems, is the multi-level security component. So does everyone know what multi-level security is? Have you ever heard of the Bella Padua model and BIBA and stuff like that? Well, that's old, military, top secret, unclassified kind of distinctions. But we've reused them in a more useful way in modern SELinux systems. You can have, on a lot of systems, you'll have a policy called the MLS policy, and it will enforce, BLP and BIBA on your policies, where you can have a process running as, system high and it has access to everything, system low doesn't, but you very rarely use that. What we use it for now is something that Red Hat termed multi-category security instead. You have one security level and you have these categories assigned to them. And the very useful things for this are, does anyone know what svert is? So svert is something that Red Hat systems do and other systems that use libvirt, where with SELinux we create a random pairing of these categories. There's 256 for one side and 256 for another. We just pick two numbers. It doesn't really matter what the two numbers are as long as they're unique and they haven't been used by a current running process. And svert will actually start the QEMU process with those categories. And it will modify all the files associated with that VM to the same two categories. And SELinux internally will only allow the access, regardless of what the policy says, if the categories line up. So if my QEMU process has categories 1 and 2 as its two categories, and my files have 1 and 2, and then I have another process with 3 and 4, it can't access my files, regardless of what type enforcement allows, because we use those categories. So there's a bunch of examples of using categories for sandboxing, using them for separation of VMs, all sorts of fun stuff like that. So that's probably the only use of multi-level security you'll see in an SELinux system. So now I've bored you to death with the really dry technical details and the clinical fundamentals of SELinux. Hopefully I haven't lost you all. At this point, I'd like to take 5 minutes and answer any questions people have that they still might be completely confused about. Because from here on, I'm going to try and go much slower, and we're actually going to do hands-on examples. Does everyone have the VM at this point? All right. Anyone have any questions? Is there anything anyone's confused about? More so than normal. All right, so hopefully at this point, we'll try and clarify some things. This is going to be the more hands-on portion where we actually try and identify what's gone wrong in our system and figure out the fundamental ways to fix them. Because really, there's very few fundamental ways in which SELinux falls down on its face. So someone said before, what does a failure look like? How do we find out we have them? So normally, if you're not running the audit subsystem on your system, every message goes to var log messages pretty much. So if you're looking for SELinux denials and you're not running audit, then they'll be in var log messages. You can easily find them by just grepping var log messages for ABC. Now, the audit subsystem, a lot of people complain about it. They say it's really heavy, high overhead. It's very useful because it allows you to do a lot of good querying and stuff like that, though. So if you're running an SELinux system and you don't have the audit daemon installed, please install it. It'll make your life a lot easier because it gives you access to this tool called AU search, which allows you to do complex queries on the audit system. So in this case, if we want to see SELinux denials within the audit system, you can just do AU search. -M is for your message type. AVC is the message type. And also, there's another set of errors called SELinux errors that are constraint-based errors and all other stuff like that. Now, the important thing to not miss at the end of this line, because it's just hanging out there, a little difficult to miss, that -I. If you do not specify that, that stands for interpret. You will get the most unreadable things in the world. You will get timestamps that make absolutely no sense to you. You will get raw system call codes instead of their actual names. Instead of getting real permission denials, permission values from Arno, you'll get just raw numbers. This makes it a lot easier to read. And for -I, it should be. Let me see. Is it supposed to be uppercase I? Oh, sorry. And you know what? I'm pretty sure someone told me that last year during my talk, and I just forgot to add it to the slide. So we do AU search, -M, AVC, SELinux, error, -I. Yeah. So the audit log is definitely protected by root permissions. So you need to execute that as root. So that's what it looks like with the I. And then if you look like what it looks like without the I, you see all sorts of, your audit timestamp's not really good. Your arc doesn't make sense anymore. syscall, it says 59 instead of the actual syscall. Instead of saying exec VE, it says, So the -I is very useful in actually looking at it. Now, you're going to tell me, because everyone does at some point, this is insane. How can I look through all this information and find out what's actually going on? There's tons and tons of stuff here. It doesn't make sense to me. Well, let's look through it and try and actually dissect what's going on. So in reality, you don't need all the parts of this. You can break it down to the small subparts and see what's going on. All your AVC denials are going to have the same type. So this top line here is all audit generic stuff. So if you start reading audit log messages, you'll just handle that stuff as it is. But the important thing to take here is we had something denied, particularly the read permission. If we wanted to find out what PID it was, we could go back and see what PID it was, the command that it was executed with, and the name of the thing it was trying to read. So that gives us a good portion of information right there, and it seems pretty easy to understand. But now we're going to get down to the SELinux. Well, actually, we're not even at the SELinux specific yet, because if for example, bash history is kind of ambiguous, so we need to know which bash history file it was. And if you really want to do that, you can crawl through, see what device it was on, find out what inode it was using find, and find that out specifically. But the SELinux specific information here is. Here's our source context, which is what we've been calling a domain type. So, for example, in this, it's saying Apache. The Apache is domain type. was trying to access a file from the admin user's home directory, and the target class, so this is the object class we were talking about, as a file. So those are the main components that you really need to know to find out what's going on with the SELinux denial. The permission, the object class, your source context, and your target context, which are the 4 components that you'll write SELinux rules with as well. Yeah?
So if we made our own VM, how do we get that to be logged? Like I just tried to access a file, I permission denied, and I have nothing in my logs.
So something that's very important to know, and it's, a lot of people start blaming SELinux before it's actually SELinux's problem. The permissions get checked inside the kernel with doing the discretionary access control checks first, and then the SELinux checks after that. So you need to pass the DAC check before you get an SELinux failure. So a lot of people are going, I'm getting an SELinux failure, I'm not seeing the error. But in reality, for example, I did this in a talk a long time ago where I did an example with Apache, and I'd forgot to set the user's public HTML directory to executable. So Apache wasn't even able to get into it in the first place with the DAC checks. And I'm sitting there going, why don't I get the SELinux error for this? Thinking that I should have gotten an error. But in reality, I failed the DAC checks. So trust me, there'll be plenty of opportunities to get denials when we write the policy, because we're going to be sitting there trying to run the program over and over and having it go, this failed, this failed, this failed, this failed, and just taking those denials and consolidating them into sensible policy rules. Yeah? Oh yeah, it's very good. So if you're running a desktop, you don't actually need to be running a desktop. I think it was Major Hayden over at Rackspace has a tutorial on this. You can have it dump the SE alert messages through email to your machine, and then SE alert can actually show them up on your machine instead.
Just tell people to send me their alert log, and
yeah.
I'll interpret it for them.
Yeah. So I'll give you the link to that later on. But you can actually set up your machines where it will dump those logs to you through email or you can do it through some other method. And it'll just have them all consolidate on your machine, and you can go through and say, oh, Sally's computer over there had an AVC log. And I'm sure Sally doesn't actually have the computer. It's some server that Sally's project is running on has the error, but So another issue, he said he didn't see a denial. I'm pretty sure it's not this case, but there's another type of rule that SELinux has called a don't audit rule, which says if you get a failure for this access, don't throw it to the audit log. Because there's a lot of poorly behaved programs out there that will just crawl through directories for absolutely no reason. And for a long time, this was spewing tons and tons of junk to the audit logs and made them unusable. So there's a lot of rules in there in the policy. There's actually a whole lot of them that say, if this access is denied, don't audit it. You can disable this temporarily. So if you're 100% sure it's SELinux that's causing this problem, but you're still not getting an audit message for it, you could use SE module, which is what you use to install and remove modules, -DB. This will remove every single don't audit rule in the policy. And all those things that are in there for a reason that are going to clog up your audit logs will all of a sudden start spewing to the audit logs. So generally what I do with this is I run the exact command that I know to fail, then I turn it back on immediately with the SE module -B command. And this will put all the don't audit rules back on. Now, this is going to be hard to decipher because you're going to have a lot of extra junk in there that you need to sift through and find out whether or not it's real. Yeah?
So in SELinux parlance, whenever you say audit, you mean write a log?
Write a message to the audit subsystem. So, yeah, so audit in this case is...
It's not the check itself.
No, yeah, it's the logging of the check. The check will always be done. It's whether or not you're notified that it failed or notified that it succeeded in the case of an audit allow message. So that's another thing that you need to be wary of when you're trying to debug an SELinux system. You're saying, I know it's SELinux. I put the system into permissive mode. It all of a sudden worked. I put it back into enforcing. It didn't work again. I know it's SELinux. I'm not getting an AVC denial. What's going on? And if that's the case, you're seeing what are called these silent denials, which can be confusing. Now, this is purely a function of the audit subsystem. This is not our fault that it works this way. So if you noticed in the earlier AVC a message that we dissected. It just said bash history, .bash history. That's very ambiguous, right? There could, on a multi-user system, there could be anywhere from 2 to 500 of these things. So we need to know what's the problem. Now, the audit subsystem will turn on what's called full syscall auditing if there is a single audit rule in place, which means when you get these denials with paths, it will show you the full path now. And the way you do this is you basically just need to set a single audit rule. So in this case, the example I normally use is setting a watch. So this rule says audit CTL, we're checking for a write to etc shadow with, I think, write or append as the permissions. In reality, audit is its own monster. There's full tutorials that can be held on using the audit subsystem properly. So, but the idea is you just basically add an audit rule in. And now we can see a better augmented denial. So it looks exactly the same as before, right? Except the only thing that's changed is we get the full name of what we're trying to access now. So that's another thing to keep in mind. Like, for example, let's say you're looking for index.html. It's not very descriptive, right? Because let's say you're a virtual host and you have 500 virtual domains set up, or even worse, you have a project that has index.html in 50 different folders. How do we know which one's wrong? Turn on the full path auditing using the syscalls, and we also get, and I guess this answers your question from a little bit earlier. You'll see audit messages with this additional kind of information on it as well. So this is the AVC. This is an additional audit message with the current working directory that the thing was run from. Ignore that current working directory because that was actually from a slide from about 6 years ago from now. So.